So without further ado, I'm going to introduce Kunal. So Kunal Mooley is a Jansky Fellow. He did his undergraduate and master's in India and finished up those in 2009. And after that, he started his PhD in Caltech, which he finished his PhD in 2015. And he worked with both Caltech faculty, with Greg Hallinan and Sri Kulkarni, as well as NRAO staff Dale Frail and Steve Myers. And he did a bunch of work on transients in the radio and other wavelengths, which you're going to hear a lot about. After he finished his PhD in 2015, he got a very prestigious Oxford Hinsey Fellowship, which he took for 2 years in Oxford. And then in 2018, started as a Jansky Fellow back at Caltech, where he is currently. And he is, you're going to hear a whole bunch of stuff about the great work and a lot of the publications that he and his team have put out in transients very recently. So without further ado, go ahead, Kunal. I'm looking forward to your talk.
Excellent. All right, so thank you, Scott, and for the introduction and for the invitation for me to give this colloquium, the first virtual colloquium that I've given. So it is an exciting time to be working in the field of radio transients, which is the primary focus of my research as a Jansky Fellow. And it is a pleasure to be presenting this topic to you today. Transients are cataclysmic events that evolve rapidly on human timescales. And examples include giant pulses from neutron stars, fast radio bursts that evolve for a fraction, that last for a fraction of a second, to supernovae and gamma ray bursts that evolve on timescales of days, months, weeks, or even years or decades for that matter. Transients have fascinated humans for centuries, with the earliest observations being carried out with the naked eye. Over the past few decades, we've developed facilities to study transients with multiple messengers, namely photons across the electromagnetic spectrum, gravitational waves, and neutrinos. In this talk, I will describe how radio synoptic surveys are bringing about a revolution in the field of transients. I'll be focusing on slow transients, those that have timescales longer than 1 second, and especially on extragalactic transients. Here's my outline. I will give some background on slow transients, synoptic surveys, and transient searches at radio wavelengths. In the second part, I'll describe how the VLA Sky survey and its pathfinder, the Caltech NRAO Stripe 82 survey, have uncovered for the first time hundreds of radio transients, ushering a new era. And I will end with presenting the contribution that radio has made to multi-messenger astronomy, specifically the electromagnetic counterparts of gravitational wave sources and especially GW170817. So since the past few decades, dedicated facilities at optical, X-ray, and gamma ray wavelengths have carried out synoptic surveys of the sky. Since these surveys have revealed actually a very interesting and rich phase space of transients that has shaped our understanding of stellar evolution, stellar death, jet physics, cosmology, also leading to breakthroughs in astronomy. Fermi and Swift, for example, find more than 100 transients every year, primarily gamma ray bursts, flaring AGN, pulsars, and X-ray binaries. The figure on the left shows how the rate of supernova discovery has accelerated since the advent of optical surveys. And within the next couple of years, we will enter an era where the LSST will find close to 100,000 transients every night. Whew, that's a lot. In comparison, synoptic radio transient surveys lag behind these higher energy surveys by at least a decade. And why is this so? Let's look at a case study, a core collapse supernova discovered in 1979 in a nearby galaxy Messier 100. The optical emission from the supernova was so bright that even amateur astronomers could observe it using a small telescope. However, it took a world-class facility like the Very Large Array to detect the radio emission from the supernova. And as a result of this, most of what we know about today about slow transients comes from the radio follow-up of objects that have been discovered in the optical X-rays or gamma rays. Here's another case study, Swift J1644, which was initially detected by the Swift Burst Alert Telescope in March 2011, where it showed intense X-ray flaring on timescales as short as minutes. Through HST and radio VLBI observations, Swift J1644 was found to be coincident with the nucleus of a galaxy at a redshift of 0.3. Radio follow-up observations were crucial for determining the radio source size, which was inferred from the radio variability because of interstellar scintillation. And together with the energetics of the event, established that there was a relativistic collimated outflow from the central supermassive black hole. And piecing together the puzzle with multi-wavelength data, it was concluded that this event was the disruption of a star, of a solar mass star roughly, by the central black hole that gave rise to a transient jet. Or in other words, this was a jetted tidal disruption event, the first of its kind to be discovered. And this technique of radio follow-up of objects discovered at higher energies has given us a good understanding of the phase space of slow transients. Here is a quick overview of the radio transient phase space spanning almost 20 orders of magnitude in timescale and 25 orders of magnitude in luminosity. Fast transients are generally found through time series analysis, and slow transients are detected in the image plane. For slow transients, we've been able to populate this phase space using dedicated follow-up of individual sources of the past few decades. However, relying on high energy triggers gives us a biased view of the of this phase space, and there is a real need for blind radio synoptic searches. So just to give you an example, up to 50% of the supernovae in the local universe remain undetected in optical searches due to dust extinction. And radio observations can probe through the dust to find the afterglows of these hidden explosions. Radio surveys are also excellent means of detecting orphan gamma ray bursts, which are GRBs, where the jets are pointed away from the Earth, and they have therefore very weak or no gamma ray counterparts, and are expected to be, in fact, 10 or 100 times more numerous than regular GRBs that are detected routinely by X-ray and gamma ray satellites. Those are the ones that have jets pointed towards the Earth. And there may be magnetically driven coherent transients that are radio bright. And therefore, only synoptic surveys can fully characterize the radio transient phase space. Now, this concept of blind searches or synoptic searches of the dynamic radio sky is not a new one. It has been attempted by several groups in the past. However, the majority of these searches have suffered from severe delays between transient detection and follow-up observations due to the use of archival data, leading to ambiguous transient classifications. Most of the searches were either narrow field or were not sensitive enough, so the transient yield has been low. And searches were also plagued by false positives like imaging and data artifacts. And the state of the art until 2012 is nicely summarized in the quotes from these two papers. I'll read them out to you. More than half of the objects in the sample have no classified counterparts and require multi-wavelength follow-up observations. We have not yet obtained any dedicated follow-up, or the scarcity of the data means that we are unable to robustly classify a large fraction of the transients. So this was state of the art until 2012. Nevertheless, there's been some success for blind radio searches. Firstly, monitoring of the galactic center around Sagittarius star has led to the discovery of pulsing source. It's an interesting one, possibly coherent in emission, having a period of 77 minutes that still remains mysterious in nature. We don't know what it is. And the comparison between the first and NVSS surveys that took place back in the 1990s led to the discovery of one radio supernova, a single radio supernova, located in a nearby galaxy NGC 4216. And there have been some discoveries also through the VLBI monitoring of nearby galaxies. And these are some examples of dust-obscured supernova, like the one in M82 pictured on the right, and the prolific supernova factory R229 found using the European VLBI network pictured on the left. So there was this paradigm of low transient yield, though, before 2012, and that paradigm changed once the receiver upgrade for the VLA was complete and the commissioning of the on-the-fly observing mode. these two innovations have been a game changer for the field of radio transients, and the VLA is now heavily contributing to radio transient science. So sensitive wide field observations of the radio sky at multiple epochs have now become feasible with the VLA thanks to these, the upgrade and the on-the-fly observing mode. The Caltech NRAO Stripe 82 survey was the first dedicated transient survey to be executed with the upgraded VLA, and that formed the core of my PhD thesis. And like many other graduate students, I began digging holes to find some treasure under the direction of my advisors. The CNSS was carried out at S-band across 5 epochs between 2013 and 2015, following a pilot survey executed in 2012. The CNSS became then the pathfinder for the VLA sky survey, which currently is being executed over 34,000 square degrees of the sky at S-band and over 3 epochs between years 2017 and 2014. These synoptic surveys are giving us for the first time a prodigious yield of radio transients and are shaping our understanding of a wide gamut of transient phenomena. So it is said that for a married couple, behind every successful man is a woman. Well, I would say that behind every successful survey is a successful pipeline, and people, of course. For the CNSS, the calibration, distributed imaging, and image mosaicing were all done using a pipeline based in ApeSlide and Python. And this was followed by source finding, catalog cross-matching, transient search, and end-to-end from the raw data to the transient search. This pipeline takes less than 24 hours for every 3 hours of VLA observing. For the VLA sky survey, the first 3 steps are of calibration, joint deconvolution, and imaging. Sub-imaging are all being executed in CASA at Socorro. And the NRAO is kindly providing VLAS quick look images. These images are fed into the second stage of the pipeline to obtain transient candidates. And the whole process of going from raw data to candidates basically takes between 2 days and 2 weeks after each observation is complete. And once we have candidates, we trigger a wide range of facilities to gather multi-wavelength data for these transients. So I'm now going to give you a sneak preview of the transients that have been uncovered in the CNSS and VLAS. And let's start with stellar explosions. CNSS 0303 was discovered in 2013 and was absent in the first survey carried out in the 1990s. This transient is located in the spiral arms of a star-forming galaxy at a distance of 120 megaparsecs. And within the host, this transient is co-located with an H2 region, which makes stellar explosion as the first suspect of what this radio transient is. The luminosity is about 10 to the 29 ergs per second per hertz, which basically implies it is more luminous than any known supernova or typical supernovae, but is comparable to the afterglows of powerful gamma ray bursts. By cross-matching the radio source position with various transient catalogs, we found that CNSS 0303 is coincident with a peculiar optical transient that was found in the SDSS supernova survey back in 2006, which was 7 years prior to the discovery of the radio transient itself. The multiband optical light curve for the transient is shown in this lower left panel. The transient is basically quite different and shows optical colors that are quite unlike the majority of the known supernovae. So it's a kind of a new kind of thing. The lower right panel now shows the follow-up radio observation from 2018 and reveals a synchrotron self-absorbed spectrum for which we can measure the peak frequency, the peak flux, and the spectral indices. And together with the distance, we can convert these into physical parameters using the equipotent prescription that has been nicely provided to us by Roger Chevalier. And with this prescription, we can basically calculate the radius of the size of the source, which is R, energy E, magnetic field B, and the density of the local ISM, N. And using these equipotent parameters, we can now paint a picture of what may be going on in CNSS 0303. We have a spherical blast wave originating from an energetic explosion that is plowing through the local ISM. As it propagates, it it shocks the ISM and produces synchrotron radiation. Using the estimate for radius, we can work out a velocity of the blast wave, which is about 10,000 kilometers per second averaged over 12 years. This is rather slow for a gamma ray burst afterglow, but it is consistent with the velocity seen in core collapse supernovae in the optical, for example. By equating the equipartition energy with the kinetic energy, basically E equals half mv squared, we can get an equivalent mass collected by the blast wave, which is about 0.2 solar masses. So taken together, these parameters imply that this event is an energetic explosion, which is sub-relativistic, that is happening in a relatively dense environment. Here's a second example. First J1419 was detected as a 23 millijansky source in the first survey from 1993 and was absent in the first epoch of the VLA sky survey, which was observed in 2017. Believe it or not, it took 23 years to find out that this bright source in first is a transient. And that's because there was no good reference epoch to compare the first survey with. And the VLAS has been extremely useful in this respect. The transient is located in a blue dwarf galaxy at a distance of 87 megaparsecs, and the high specific star formation rate of this galaxy suggests that this may be a stellar explosion. The luminosity of the radio source is few times 10 to the 29 ergs per second per hertz, again, much more luminous than typical supernovae. In the lower left panel here is the light curve spanning 27 years, plotted using archival data from 4 different telescopes. The lower right panel shows the broadband radio SCDs or spectra over 4 different epochs between years to 1993 and 2019. It shows the evolution of the synchrotron self-absorption frequency, which is basically moving towards, which is basically decreasing as time progresses. We can again calculate the physical parameters associated, assuming energy equipartition. And for the 2019 epoch, the radius estimate implies that the source size is a fraction of a parsec. This is incredibly close to the recently measured size using the European VLBI network, which is about 3 milliarc seconds or about 1 parsec at the distance of the host. So in our synchrotron blast wave picture, then we find that the radio data from 1993 and 2019 imply average velocities of 100,000 kilometers per second and 50,000 kilometers per second, respectively, or about 30% and 15% the speed of light, which is extremely large compared to typical supernovae and possibly implies the presence of a central engine, such as a magnetar or jet that is powering the stellar explosion. This third example is fresh out of the oven, discovered last month in the ongoing second epoch of the VLA sky survey. It is located close to the nucleus of a blue dwarf galaxy at 60 megaparsecs, and the implied radioluminosity is around 10 to the 28 ergs per second per hertz, which is at the tail end of the radio supernova distribution. By cross-matching the radio source position with different transient catalogs, we found that this transient is the afterglow of a supernova that was discovered in the optical in December 2019, so about 10 months ago. 3 weeks ago, we obtained an optical spectrum which shows broad features, broad emission lines basically associated with forbidden calcium and oxygen lines, indicating that this the shock is or the gas is moving at velocity of a few thousand kilometers per second and interacting with the surrounding dense medium. And these spectral features are consistent with a type 2b supernova classification, which means that this explosion comes from a massive progenitor star that was partially stripped of its hydrogen envelope due to binary star interaction. The lower right panel shows the radio follow-up spectrum from last week. The equipartition parameters again suggest that the blast wave is energetic and is running into a dense medium. So the implied velocity now, if we calculate using the equipartition estimate for radius today is around 25,000 kilometers per second, which is consistent with the initial velocity that was inferred from optical spectroscopy carried out in December 2019. So we can piece together the puzzle now again for this transient is that it comes from a supernova explosion of a Wolf-Rayet star, which is one of the most massive kind of stars known, that has shed part of its hydrogen envelope prior to the explosion, and the synchrotron blast wave is running into this shell that has high density and is giving synchrotron radiation. So we understand from these discoveries that the radio-selected population of stellar explosions is special. It is best seen in this energy velocity diagram where the shock velocities and the energy contained in the shocked gas for a variety of radio supernovae are shown. Standard core collapse supernovae are shown as black circles, and the so-called type 1b Cs, which are stripped envelope supernovae, are shown as black in blue squares. And some of the dust obscured supernovae or hidden supernovae that were found previously by radio surveys are shown as yellow diamonds. The slant dashed lines that you can see running across this plot are estimates for the mass of the shocked gas, which is basically equating energy and half mv squared, so the kinetic energy. Transients discovered in the CNSS and VLA sky survey have the highest energies on this plot, implying that radio surveys are now revealing new populations of energetic stellar explosions. And we have only just started seeing the tip of the iceberg. Moving on to tidal disruption events discovered in these radio surveys. This one is CNSS 0019 that was discovered in 2015 while the CNSS survey was ongoing. And this plot is showing you the light curve at 3 gigahertz. The inset there is the SDSS image cutout in the optical. And we see that the transient is located in the nucleus of a lenticular galaxy at a distance of 77 megaparsecs. So we obtained VLBI follow-up observations, actually VLBA observations, which shows that the position of the radio source is consistent with the Gaia position, or the precise optical position of the source, to within 2 milliarcseconds, or basically it implies that the radio source is located within 1 parsec of the host nucleus. So it is most likely associated with the nucleus, the supermassive black hole. The right panel now shows the VLA follow-up spectrum or spectra taken over multiple epochs between 2015 and 2017. And that also shows the synchrotron self-absorption peak, which is evolving and decreasing as time progresses. By calculating the equipartition parameters now, using these synchrotron self-absorbed spectra at multiple epochs, we can calculate a shock velocity of about 15,000 kilometers per second, energy of about 10 to the 49 ergs, and an ejecta mass of about 10 to the minus 3 solar masses. So it appears that a star ventured close to the supermassive black hole, got ripped apart, and this tidal disruption event somehow launched an outflow that is giving rise to the radio emission. And how this outflow and radio emission are arising is still a matter of debate. In one theory, which is the disk wind explanation, part of the gas from the star basically remains bound and forms an accretion disk, and radiation pressure drives the gas out from the disk, basically a disk wind of some sort that can collide with the ambient medium to give synchrotron emission. In the collision-induced outflow theory, the loosely bound material from the star may fall back in parabolic orbits, and the different streams of material may collide and result in an outflow as their orbits precess around the supermassive black hole. In a third explanation for radio emission, a very close encounter between the star and the supermassive black hole can impart momentum. So you can imagine like a recoil, the star passes extremely close to the black hole, and that imparts momentum. So it just travels much faster outwards than it had, the momentum it had when coming towards the black hole. And so this can impart momentum to the unbound tidal debris, which generates an outflow with a fairly large opening angle. And using late-time VLBI observations of radio TDEs detected by the VLAS, I think we will be able to distinguish between these scenarios and solve this open question. Now, irrespective of how these outflows are generated in TDEs, we can use the radio emission to probe the radial density profiles in the nuclei of the host galaxies for these TDEs. And this has already been done in a few cases. In this figure, the gas density is plotted as a function of radial distance from the central black hole, supermassive black hole, in units of Schwarzschild radii. It is seen that while some galaxies, including the Milky Way, which is pictured on the left side of this plot, have a shallow density gradient, which is consistent with a radiatively inefficient accretion flow, or RIAF, in short, as it is called. Whereas in many other cases, it is found that TDs like CNSS 019, for example, show that the host galaxies have steep gradients in density, nuclear density, which basically might be indicative of strong winds from young massive stars that are residing in the nuclei of these galaxies. So that's sort of the steep spectrum that we are seeing with the density profile, and which may be very likely related to massive stars residing in the nucleus. So last but not the least is a sneak preview of AGN. CNSS 0138 was discovered in comparison between CNSS and FIRST surveys. It was not detected in FIRST, but had a flux density of a few millijanskis at 3 gigahertz in the CNSS survey. And this source is a quasar located at a redshift of 1. Follow-up VLA spectra from 2016 and 2019 reveal a gigahertz peaked spectrum, which is typical of a young radio AGN. The spectra also show that this source has increased in flux density by at least a factor of 5 over the past 18 years and is now stable to some degree at least a few gigahertz frequencies. And so we can also look at the optical behavior for this source using nice coverage of optical spectroscopy that exists over the past 20 years from, thanks to the SDSS and follow-up spectra that we took using the Keck also. So anyways, these data are indicative of strong changes that are in the UV optical continuum, and also the broad line, specifically the magnesium line, indicating changes in the broad line region as well. So basically, these data suggest that the radio state changes, or the radio changes, are occurring. They coincide with these changes in the accretion level, most likely the enhancement in accretion onto the supermassive black hole. And as a consequence, the quasar underwent renewed AGN activity, possibly also transition from the radio quiet to the radio loud mode. And VLBA data are consistent with the young jet interpretation and reveal a core jet structure having a linear size of about 20 parsecs. CNSS 2330, this is another example, not detected in the first survey, but has a flux density of close to 10 millijanskis at 3 gigahertz in the Celtic area Stripe 82 survey. This is also a quasar located at a redshift of about 1.6. Follow-up VLA spectra between 2012 and 2019, so spanning several years, again reveal a gigahertz peaked spectrum in the, actually in the 2016 and 2019 spectra, the source appears to be flat spectrum beyond about 4 gigahertz. So there's some sort of a transition going on there within this radio source. Optical spectroscopic data from 2012 and 2017 indicate dramatic changes in the optical continuum emission. And this likely also now suggests that the radio state changes are maybe correlated in some ways. Again, one needs to do a more quantitative analysis, but these radio state changes might be related with changes in the accretion state of the quasar itself. And with the VLBA, we basically see an unresolved point source, so it's compact on milliarcsecond scales. All these data now again suggest that CNSS 2330 is undergoing some renewed jet activity, likely associated with this enhanced accretion episode. A famous astronomer who happens to be one of my PhD advisors, in fact, has said that AGN are vermin in the transient sky. I would argue that AGN are valuable probes of accretion and jets, analogous in some ways, possibly to X-ray binaries. And using the sample of renewed AGN jet activity, we can do this interesting order of magnitude calculation using the rates of these AGN. We see approximately 2 such AGN brighter than about 3 millijanskis over 100 square degrees of the sky at any given time, and assuming a time scale, a rise time scale for these for the radio emission, which we've seen between like the first and CNSS survey, to be around 20 years, we can calculate a period of recurrence of this jet activity to be around 40,000 years. So therefore, what I think is happening is over the lifetimes of these AGN, these sources actually undergo episodes of enhanced accretion and therefore enhanced jet activity once every tens or hundreds of thousands of years, which is quite small compared to what we were talking about several years ago, or actually decades ago, that the lifetimes or the timescales over which jets change is like millions of years. So that was just a sneak preview of a much larger sample of transients that we are finding in the VLA Sky Survey. And this is a gallery of image cutouts for some of the nuclear transients associated with renewed AGN jet activity or tidal disruption events. And here are some off-nuclear transients associated with stellar explosions. And within this sample, we also hope to find orphan gamma ray bursts and other exotic transients. All these discoveries are helping us answer important astrophysical questions like what fraction of supernovae go undetected in optical surveys or basically are hidden explosions? What are the mass loss histories of supernova progenitors? What fraction of stellar explosions harbor central engines like magnetars or jets, basically pumping energy and causing the explosions of stars? What is the fraction of tidal disruption events that launch jets? And what are the properties required for jet launch? Actually, that's a fundamental question in jet physics that we haven't been able to answer so far. What are the properties that are required to actually launch a jet? And what are the rates of long gamma ray bursts and neutron star mergers? Now, changing gears just a little bit, in maybe the last 10 minutes, I would like to tell you how important contributions have been made by the radio to multi-messenger astronomy, specifically the events discovered by LIGO and Virgo gravitational wave observatories. We have a VLA large program to search for and study the radio counterparts of gravitational wave sources. And this program is called the Jaguar, which stands for Jansky VLA mapping of gravitational wave bursts as afterglows in radio. With Jaguar, we've carried out blind searches to look for the radio counterparts of a few binary black hole mergers reported by LIGO and Virgo over the past 5 years. And this figure gives an example of a narrow deep search. The sky projection on the left shows the localization region of the gravitational wave event. The middle panel shows the localizations of ice cube neutrino event and a Hawk gamma ray event that may possibly be associated with this merger. And to the right is the pointed mosaic as observed with the VLA at C-band or 6 gigahertz. So the figure now at the bottom is an example of a wide shallow search over 200 square degrees. The left panel shows the localization region of the black hole merger, and the right panel shows the VLA on-the-fly mosaic image. Although we haven't had any success with detecting any radio counterparts for binary black hole mergers, we were able to nail down the counterpart for the binary neutron star merger GW170817. And this is a timeline of events as they unfolded. The gravitational waves from the merger arrived around 12 noon, 12 p.m. GMT on the 17th of August, 2017. A low luminosity short duration gamma ray burst was detected with Fermi and integral satellites around 1.7 seconds later. An intense optical search, actually search with optical telescopes across the globe to find the optical counterpart, which was finally nailed down 11 hours after the merger. And that was followed soon after by detections in the near infrared and ultraviolet. Despite repeated searches in the X-rays and radio, no counterpart was found until 9 days when Chandra detected the X-ray afterglow. And radio searches continued fervently, and finally 16 days after the merger, an extremely faint radio counterpart, in fact, was maybe 4 sigma, where we announced it for the first time to the astronomical community. It was about 15 microjanskis, so quite stretching also to the limits of the VLA with the Jaguar program. This is a panchromatic view of GW 170817 over the first 100 days after the merger. The optical transient called the kilonova was powered by thermal emission arising from the R process nucleosynthesis. It showed a rapid blue to red color transition, which was quite different from other kinds of transients, and faded on timescales of a few weeks. The rapidly evolving kilonova signal implied that a roughly spherical shell of neutron-rich material was ejected from the merger at speeds around 10 to 30% the speed of light. On the other hand, the slowly rising radio emission implied a mildly relativistic wide-angle outflow having significant angular structure. And this was basically seen almost for the first time. I mean, all these sort of data implied some new kind of an event that was new kind of transient that was associated with the merger. And this was an important result. This wide angle mildly relativist outflow basically meant that the prompt gamma ray signal that arrived 1.7 seconds after the merger also originated in this mildly relativistic outflow, which is quite unlike typical GRBs, gamma ray bursts, where the prompt emission comes from the ultra relativistic outflows. Now, this wide angle outflow shown in red here, also called a cocoon, would naturally arise from the interaction between a relativistic jet, which is shown in yellow, the conical structure here, with the neutron-rich ejecta, which is shown in blue, the spherical sort of structure. I've also shown the line of sight to the Earth. So this was as events were unfolding, basically in 2017 or 2018. But there was a big question, especially in the GRB community, and that was whether the putative jet successfully penetrated the neutron-rich ejecta or got completely choked by it. So you can see the two scenarios here that the debate was going on out of. There's also this large body of papers that I've included at the bottom that discussed at length about this issue. The choke jet, successful jet issue was also hotly debated in scientific conferences worldwide. And just because answering this question was just so important, it had a lot of astrophysical implications, such as the link between regular short gamma ray bursts and neutron star mergers, the gamma ray emission mechanism, and the detectability of electromagnetic counterparts of future gravitational wave events. And the controversy was finally resolved through radio VLBI observations, where we used the high sensitivity array comprising of the very long baseline array, the phased VLA, and the GBT telescopes. So all these three together. We thought that this would give us an extremely high resolution snapshot of the radio source, and we could directly study the morphology of the relativistic material. Although we could not resolve the radio source, what we saw with the VLBI was quite spectacular. The radio source was compact and showed a proper motion of 2.7 milliarc seconds over a span of 155 days. So these observations were carried out on day 75 and day 230 after the merger, and in the plot you can see that the radio source position has actually moved, implying a proper motion, which basically means that we are seeing superluminal motion 4 times the speed of light. And the superluminal motion was the smoking gun of a presence of a successful jet. So a jet was in fact produced after the merger, and it successfully penetrated the neutron-rich material. And the motion of the jet was what we were detecting with VLBI. By confirming the presence of the jet in GW 170817, we finally had strong observational evidence that neutron star mergers are actually related to short gamma ray bursts. Using detailed hydrodynamical modeling or simulations to fit all the observational data, we were able to obtain precise constraints on the geometry and properties of the jet, and the properties also of the circumburst environment, of the local environment of the merger. We find that the jet opening angle has to be less than 5 degrees, and the viewing angle, which is basically the angle between the line of sight and the direction in which the jet was launched, was between 15 and 30 degrees. And it turns out that the energy of this, the isotropic equivalent energy of this event was quite large, in fact, at the tail end of the short GRB distribution. But when you correct for beaming effects, it basically confirms that it is consistent with short GRBs in the sense that it is between 10 to the 49 and 50 ergs. Now, using tight constraints on the geometry together with information from the gravitational wave signal itself, we were able to get a precise measurement also of the Hubble's constant. So the value that we got was 70.3 plus or minus 5.3. It's not as precise as, let's say, the Planck or type 1a supernova sort of measurements. But over the next few years, we think that we can basically reduce the or increase the precision of these measurements as we get more and more neutron star mergers in our sample. And hopefully give at the end of this decade, maybe give a model independent estimate of the Hubble's constant. So this simulation shows the aftermath of GW 17017 of what we think happened. This shows the neutron rich ejecta at the bottom, the spherical sort of structure, and the jet propagating along the vertical axis. So the jet successfully broke out of the spherical ejecta and is dragging some of the neutron-rich material along with it. That is driving this wide-angle outflow that you can see propagating in the vertical direction. This wide-angle outflow or cocoon is what we see in the radio or in the afterglow signature for the first 60 days, and the jet core dominates at later times. Okay, so GW 17017 was a success story, but we haven't detected any other electromagnetic counterparts since 2017. And this is because the localization regions for gravitational wave sources currently span more than hundreds of, span basically hundreds of square degrees on the sky. The upper left panel here shows the current capability of localizing a test source that might be located at different parts of the sky. But just in the next few years, the addition of LIGO India to the network of gravitational wave observatories will make the sky localization regions shrink by an order of magnitude. And this will give a competitive edge to radio telescopes like the VLA that have high snapshot sensitivity, but small fields of view. In the meantime, Jaguar is evolving into a collaboration between the major radio facilities across the globe to undertake coordinated follow-up of gravitational wave sources, and more generally of radio transients. This coordinated approach ensures that we make most efficient use of the limited time that is available at the different observatories. And these radio facilities are also doing their own surveys to find slow transients. The VLA has VLAS, ASCAP has a program called Variability and Slow Transients, or VAST, Meerkat has Thundercat, and wide field surveys are also underway with the aperitif feeds on the Westerbork array. And 5 to 15 years from now, maybe we will be in a position to execute synoptic surveys routinely with next generation facilities like the Square Kilometer Array, the NGVLA, and the Deep Synoptic Survey that is currently being planned at Caltech. And these will be capable of producing several transient alerts every single day. So I'd like to summarize the talk now and bring you back to the radio transient phase space. Highlighted in red here is the region where the CNSS and VLAS are contributing in terms of discoveries. The surveys are uncovering new populations of transients, such as energetic stellar explosions, that are revealing the mass loss histories and central engines that might be driving these explosions. Outflows from tidal disruption events that can be used for probing circumnuclear environments, and renewed agent activity on 10 to 100,000 year timescales. And hopefully soon within the VLAS, we will also start finding other classes of transients like orphan gamma ray burst afterglows. Observations also have been extremely useful in understanding the astrophysics of gravitational wave event, which was the binary neutron star merger, GW 170817. The radio afterglow of this merger almost uniquely probed the morphology of the jet and its energetics and the density of the merger environment, the local environment around the merger. And the constraints on the viewing angle or the geometry led to a precise measurement of the Hubble's constant. Radio facilities across the globe are now executing surveys to find new slow transients, and I'll leave you with some of the open astrophysical questions that these surveys will answer in the coming years. I thank you for listening to this talk and will be happy to take questions. I put my email address down at the bottom of the slide if there are any overflow questions. So thanks a lot for listening and happy to take questions.
Great, thank you very much, Kunal, and applause all around, even though you probably can't hear any of it except for just me. But thank you very much for a really nice talk. So for people, right now there are no questions in the question and answer box, but feel free to type some questions in there. And also, since we don't have anything backed up, if you want to ask a question, feel free to use the raise hand button as well, and I can call on you and give you a chance to talk. And while you're doing that, I have a question for you, which is, so I'm curious with the, with these new radio surveys, especially VLAS now with the multi-epochs coming online, is there any sense on what the false positive fraction of your transient events that you're seeing are due to imaging artifacts or RFI or whatever? I know that those have kind of plagued some of the earlier radio transient searches, and I was just wondering whether things are better or worse nowadays.
Yeah, so if you just go by the sort of pipeline structure that I showed you, then the false positive rate is extremely high. Maybe one transient versus two false positives, even if you can say. I think that's just because, I mean, these are sort of quick look images, and one has to do very detailed and quite a bit of effort if you want to reduce the artifacts in the image, and most of these end up to be side lobes actually. So what we end up doing is just manually inspecting each and every image, and then basically see which ones of these would be real versus false, and then follow those up. But I mean, going forward, I think machine learning is the way to go to reduce at least the number of false positives, and some of these efforts are going on at Caltech here.
Great, thank you very much for that. Other questions from anyone? I do see we have a question from David Nichols, so I'm going to let David talk. You should be able to unmute and talk now, David.
Yeah, can you hear me?
Yep.
Okay, great. Yeah, so thanks for the very nice talk. I was curious if you could comment a bit on what the prospects are for detecting radio transients from neutron star binary mergers in O3, where there haven't been any optical counterparts that have been found to help localize the sources.
Yeah, so, well, the sort of examples that I showed you in one of the previous slides basically showed, it was just telling you that, I mean, we did these wide field or pointed searches, galaxy pointed searches, but there was basically the error regions or localization regions of the sky were way too large for the VLA to contribute significantly. So unless these shrink over the next set of runs, the immediate one, which is 04, that will begin in 2022, I think the localization regions will still be large. So until 2025, I think it'll be hard to find a lot of electromagnetic counterparts. But starting with LIGO India, when that comes online, I think that's really going to be exciting, because the localization regions will then shrink down to like 10-ish square degrees. And we already have radio facilities to go after such events, like ASCAP, for example, has 30 square degrees. So we can dig deeper. Meerkat also has an excellent point source sensitivity and has a 1 square degree field of view. So these telescopes can really step in and do deep searches that that can detect afterglows like GW170817, which was quite faint, in fact. So I think it's possible, but we'll have to wait for a few more years until we start finding a lot of these.
Okay, thank you.
Great, thanks for that. And we have a question from Ilsang Yoon in the Q&A box. And that question is, what is the current best practice to find out or confirm the optical counterpart for an off-nucleus radio transient?
Interesting question. I think we'll need multi-wavelength data. We'll need probably a lot of a lot of information that we need to piece together, I think, before we can confirm an off-axis event. I mean, GW170817 was the first of its kind. People have claimed that of detections of off-axis events previously, but I mean, none of those are like definitive. This is the first definitive one, but it was definitive because it was first found through gravitational waves. So it'll be hard. And looking at the host galaxies, looking at various energetics, and I think radio is the way to go because I mean, the sort of broadband spectra between, let's say, radio, optical, and X-rays will tell you a great deal about what is going on with these sources, whether they are off-axis or whether they are just complete off-axis jets or something completely different. So I think, yeah, a few different pieces of information will need to be used before we can conclude that we are starting to find off-axis afterglows.
Yeah, and as a potential clarification, I think the question was about off-nucleus radio transit. So I think
off-nuclear. Sorry,
yeah,
I thought it was off-axis. Off-nuclear, and the question was about confirming them.
Confirming the optical counterparts. Yeah.
Oh, confirming the optical counterparts. Well, what we're doing right now is just looking at previous archives for optical transients and see whether they basically lie within one synthesized beam of these radio positions. So that's all we are doing. And maybe if one wants to do something more fancy, like what we did with Gaia and VLBA for one of the tidal disruption events that I showed, something like that could be done, like a Gaia source position versus VLBA observation of the radio source to see if that might be coincident. But it may not be easy because if we end up finding optical counterparts, some of them might be very old. Optical counterparts might be old. So I mean, it may not be very easy in all cases, but I think it's possible to do.
Great, thanks for that. Any other questions for the last minute and a half? Going once. All right, so thank you very much, Kunal, and thanks for everyone for attending the first virtual of our colloquia. I think it actually went quite well, and thanks for a really, really nice talk. And just a reminder for the students, the link that just was in the chat a little bit ago and also got emailed to the UVA grad students, Kunal will be in there in just a few minutes to chat with you guys. So thanks a lot to Karen and to the speaker and to everyone else for helping to organize. Cheers, everyone.
Thank you, Kunal.
Thank you.